Hey, welcome back. We are in 2.3, which is sets and compound inequalities. So we'll first talk about a set. A mathematical set is simply a collection of mathematical things. So math is very definition driven. A set has a definition. It's a collection of stuff. And this is kind of the bottom of the barrel where all of a sudden definition starts not meaning anything. These things could be numbers, they could be letters, they could be ideas, they could be operations, they could be any number of things. So we stop at some point defining stuff and just say, well, there's some junk in there. We're just going to call that the stuff that's in the set. And these things are called elements. So it's just a collection of objects. We're going to call those elements, right? And again, they could be a great number of different things. We're going to stick to pretty simple ideas like numbers, right? Our sets will be numbers or letters or, pretty basic stuff like that. So let's take a look at a set. A set might be denoted by a capital letter, typically a capital letter, to indicate that there's some, largeness to this idea. There's some stuff in there, right? And you would sometimes just list out what's in that set. Like if I have a set A and it's just a bunch of numbers, I'll write those numbers. There's a set. There's stuff in it. It's just that collection, right? When we write out a set is just identifying what's in the set. So it'll only appear once. Like the number 3 will only appear once. The number 5 only appears once. Whatever's inside this set is just a list of what's there. Writing it out like this is called the roster method. And it's exactly that. It's a roster. It's a list. You go to the baseball game, you got the roster. It's literally a list of the dudes that are going to hit the ball, right? That's what this is, just a list of all of the stuff in the set. Right? It doesn't necessarily, again, need to be numbers. It could be letters, right? Or it could be a combination of both. Right? We might also have, let's say, let's write this. Write the set containing all months of the year that have an O. Is that a good idea? January, February, March, April, May, June, July, August, September, October, November. There's 2 of them. All right. O in them in roster order, or through the roster method, right? Call it whatever you want. Call it M for months, right? It doesn't matter, but M is the set that I'm denoting. I always open up a set with a curly bracket, right? This indicates this is a set. The months that have an O in them, unless I missed one, there's October and November. That's it. That's my set, those two, right? List, kind of in the same fashion, the set containing, in this case, let's say days of the week. containing, let's say, a T. Call it D for days of the week, right? A lot of times if you're at liberty to choose your letter, sometimes to choose it in a way that you can remember why you chose that letter. D for days of the week, M for months, right? Containing a T, we got not Sunday, Monday, well, Tuesday's in there. Not Wednesday, but we've got Thursday. There's no Friday, but there's a Saturday, right? Because there's a T on Saturday. And there it is, there's our list. That is our set. Suppose we have two sets. A is, I'm going too high a little bit. A is one of these sets. Containing 1, 3, 7, 21, 42, and 100. Now let's say we have another set B, which is say 2, 4, 7, 10, 42, 100, and 200. Okay. We have two sets, right? We can describe a conjunction of these two things. Let's call the first one the union. The union of A and B, denoted as A, kind of elongated U, B. Right? A union B is the notation for the union, right? Is a new set composed of all of the elements from A or B or both A and B, right? So it's basically everything. We're taking everything from A, we're taking everything from B, we're chucking it into a barrel, and we're calling it the union. Everything that's there is now a new set. But again, when you write these sets, you only want to write each element one time, you don't want repeats. So if I were to write A union B, once again, A union B is a new set. And it's just everything. It's 1. I'm going to do them in order. That way, well, I mean order, because if you don't, it's chaos, right? I have 1, I have 2, there's a 3, a 4, 7 appears in both of them, but I'm going to write it once. All I need to know is that it's there. I don't need to write that it's twice because it's in both. I just need to know that it's there. So 7 and then 10 and then 21. 42 appears in both, so I'll again only write it once. 100 appears in both. Again, I'll only write it once, but then 200, and that is the union. It's everything put into the same basket, if you will. Think of it as this way: Class A, Class B, right? Class A has these people in it, Class B has these people in it, in this case represented by a number. And you said, list all of the people that are in these classes. You wouldn't say, oh, Fred's here, Albert's here, Jill's here, Mortimer's here. I don't know where these names are coming from, but you wouldn't say, oh, and Jake is here, but Jake is here again. No, I just want to know if Jake is here. I don't care if he's in both. He's just here. And so he's in the list once. Okay? So that's a union. There's another conjunction here. And that is called the intersection. The intersection of A and B. And the intersection is written similarly to the union, but we're going to take that U and flip it upside down. So that is to say A, the U gets upside down, that indicates that it's an intersection instead of a union. A intersect B is also a new set, composed of only the elements that are in both A and B. Right. So the union is very, come on in, welcome, everybody walk into the room and meet each other, right? The intersection is very exclusive, right? It's only going to be composed of the elements that are in both groups, right? So again, if I go back to that classroom model, I have class A and class B. A intersect B is, tell me all of the students that are taking both classes. That's all I want to know, right? You can think of it as the intersection of a road. There's road A, there's road B. The intersection is literally that part that's part of both of them. That's the intersection, the rest of this junk is not, right? So if I want to write the intersection of A and B here, I would have A intersect B is equal to, and then it's just the ones that are in both. So we ran across those. 7 is in both, so it's in the intersection. 42 is in both, and then 100 is in both. So it's a much smaller list. There it is. And that is the intersection. All right. Let's take a look at maybe another example of this. You'll see questions like this. Let's give two sets. Let's say I have A is, we have some numbers, that's a bad bracket. And we might have some letters in there. Right. A is 1, 2, 5, A, B, D. Let's say B is 2, 3, 5, B, C, D. So you might be given these, and you might be asked to then find A union B, and you might be asked to find A intersect B. Right. Well, A union B is just a list of everything, throw it into the barrel and pick out the duplicates and eliminate duplicates, but that gives me a 1. I've got a 2, so I'll just write it once. I don't have to write it twice. There's a 3, so there's a 3. 5 appears twice, but again I write it once. There's an A, B, C, D. Right? All of these guys are all of those guys. Right? The intersection, however, is only the ones that appear in both. So 2, 5, B, D. And that's it. Those are my intersections and my my unions and my intersections. Now, this whole idea translates over into inequalities, right? What we're doing here, all of this has been discrete, meaning that there's a finite number of elements, right? But a set may not necessarily be finite. It may be, all of the numbers between 0 and 1. And not just the integers, not just 0 and 1, I mean like a half, and a quarter, and a third, and a fourth, and a fifth, and a sixth, and there's literally an infinite number of numbers between those two. And so we call those continuous. So we might have, let's say, one set is all the numbers greater than 5. X is greater than 5, right? And so another one might be x is less than negative 3, and this is one of the examples from down below. Right? So I can call this group A if I want to. We kind of lose that notation a little bit, but they are not group, but sorry, set A, and this we would call set B, and I wrote that too high, I realize. We kind of lose the notation a little bit when we start dealing with these, because it's easier just to say, well, we know it's a set, let's just call it this limitation that identifies what the set is, right? But if I have these two sets, right, I can no longer use roster method anymore, because roster method lists out every single element, but I can't do that, right? What are the numbers greater than 5? Where do you start? 5.1. But there's a number smaller than that that's still in the set, like 5.01 or 5.001, and you cannot list them, right? Can't do it. So we start just leaving it like this. This is another way of writing a particular set. And I have two compound words that we're going to use with these inequalities. So when I see the word and, right? This is the intersection. Find the solutions to this and this is the intersection of those two sets, right? So if that's what I'm asked for, if I have to meet those two limitations here, then x is greater than 5 means all of those numbers starting here at 5, open circle because it's strictly greater, and that way. This is my set, all of those numbers. Right? The other one, this x is less than negative 3, is an open at negative 3 and everything to the left, right? So when I say and here, I'm looking for all of the numbers that are both greater than 5 and less than negative 3. And there aren't any. And you can pictorially see that because if I push these two together, I'm looking for the numbers that are in both, that are highlighted in both lines, and there aren't any. So, and means literally the x is greater than 5 intersected with x is less than negative 3, but that's nothing. There's nothing there. The empty set, right? There's nothing in it. Right? So that's what an and is that intersection. We'll see some intersections that aren't empty, but let's take a look at or. Or is the union of these two sets. Right, if they come along and say solve this, x is greater than 5 or x is less than negative 3, now I don't have that limitation where you have to be in both. It's one or the other or both, right? Which means that I have all of these guys from negative 3 off to the left, and I also have those guys from 5 off to the right. And they're disjoint because there's a separation between the two, so I can write that simply as a union. That'll be all of the numbers between negative infinity up to negative 3, with a parentheses on the negative 3, and then I just union that with 5 to infinity. and that's our or, meaning unions. All right, we'll stop this video right here. I'm going to do a couple of examples from this on the next one, and that'll just be right below.